Start, sir?
Yes, we can start.
Okay. So, first of all, respected Dr. Kazuyuki SEKIZAWA, Dr. Sukhjit Singh, my respected colleagues in the department, dear students, Waheguru Ji Ka Khalsa, Waheguru Ji Ki Fateh. So today we have a very interesting talk to be delivered by Dr. SEKIZAWA, and we are highly grateful to Professor Sir for delivering this webinar on the topic of a journey through the wonders of physics with the atomic nucleus. So I would like to welcome all the students and all the scholars who have joined us for this webinar. And this webinar, as it is reflected from the topic itself about atomic nucleus, and though it is a very tiny massive entity which is said to be atomic nucleus composed of protons and neutrons, but despite of its tiny nature, due to this stark contrast to its small size, physics of atomic nucleus is so diverse, and it is closely related to particle physics, condensed matter physics, astrophysics, as well as cosmology. So it will be definitely fruitful to all the scholars who have joined us from these areas as well. And I hope that they will take full benefit out of this discourse on the said topic. And I welcome you all once again. And we are grateful to Professor SEKIZAWA for this talk. And now I would like to request my colleague, Dr. Sukhjit Singh, to kindly introduce speaker of the webinar, Dr. Sukhjit Singh.
Thank you, Dr. BirBikram Singh. It is my proud privilege to welcome and introduce a very young and energetic professor, Professor SEKIZAWA from Tokyo Institute of Technology, Tokyo. Regarding his qualifications, he did his 4-year BSc in 2010, very recently from Tokyo University, and MSc in 2012 from University of Tsukuba, Japan, and PhD in 2015 from same university, University of Tsukuba, Japan. And during the period of 2015 to 17, he worked as a research assistant professor at Warsaw University of Technology, Poland. During 2017, he worked as a research associate at University of Washington, Seattle, USA. During 2018 to 2021, he was specially appointed as an assistant professor by Niigata University, Japan. Since April 2021, he is working as an associate professor at Tokyo Institute of Technology, Tokyo. And with effect from April 2018, he is also collaborative fellow for Division of Nuclear Physics at the University of Tsukuba, Japan. Professor Tsukuba won many awards during the last 10 years, and some of the major awards are Best Participant Award of 2013, Terran Force 6. In 2014, he was awarded as an Excellent Achievement Award. Again, in 2014, award for Best Project 2014, Terran Force 5. 2015, award from Dean of Graduate School of Pure and Applied Sciences, University of Tsukuba. In 16, 10th Young Scientist Award by Physical Society of Japan. 2017, award from the Rector of Warsaw University of Technology. December 2017, Group Thesis Award. In 2018, he was awarded by 2 prestigious honors. First one was the Nakamura Prize, and second was the Excellent Achievement Award. And 2019, he was awarded with the 6th Niigata University Rector Award. And very recently, in December 2021, he was awarded with the promotion of earlier career research in School of Social Sciences by Tokyo Institute of Technology. He is a member of various highly learned bodies and has contributed more than 100 such articles in terms of journal publications, conference proceedings, presentations in various national and international highly reputed nuclear physics events. Without taking too much time, I request Dr. SEKIZAWA, please deliver your talk.
Okay, thank you. So let me share my screen. Okay. Can you see the screen?
Yes, yes.
Okay.
Yes, so we can
okay.
see it.
Okay, let me start. So first of all, thank you so much for inviting me for this seminar. It is a great pleasure to deliver my talk at Akal University. So, and thank you very much for the kind introduction. Okay, so my name is Kazuyuki SEKIZAWA from Tokyo Institute of Technology. Okay, so today I'm going to talk about our journey through the wonders of physics with atomic nuclei. Okay, and so I think I can skip this. So I prepared a brief introduction of myself. So as introduced, so in short, I got a PhD degree at the University of Tsukuba in 2015, and then I spent 3 years in Warsaw and Seattle in United States as a postdoc. And then I come back to Japan as an associate professor. And then from last April, I got a position as an associate professor at the Tokyo Institute of Technology. And now I have my group and I have students. And yeah, we are trying to understand better the physics of atomic nuclei. Okay, so the main research field is nuclear theory. And today I will talk about the nuclear physics, which I don't know if you know some information about the nuclear theory. So by the way, so let me ask one thing. So now how many students, I mean, bachelor course students and undergraduate course students and graduate course students are listening this seminar? Depending on it, I will change the details. Are there many undergraduate course students?
Sir, yes, there are undergraduate as well as postgraduate students, and also students from the other universities, not from the Akal University. External participants are also there. Maximum number is undergraduate and postgraduate students.
Okay, so I will keep my talk more, general one. Okay.
Yes, yes. And faculty members are also attending from the various systems.
Okay, thank you.
Yes.
So let me start. Okay. So, okay, as you know, since you are in the physics course, the fact that physics deals with everything in nature. Okay, so not only the very tiny scale, like elementary particles like quarks and gluons, and also we also study the molecules or atoms, and also some materials like metals, conductors, semiconductors, and so on. And in addition, we also study some astrophysical phenomena, and also the most largest scale, we study the structure and the origin of the universe. Okay, and here today's topic is this one, atomic nucleus. So it is not an elementary particle, but some structure, and it has some structure, but it is very tiny object. So within an atom, it is just a point at the center of the atom, but it has some massive object. Okay, so this is today's key object I'd like to discuss in this seminar. So let me start with very introductory introduction. The size of an atomic nucleus. Okay, so I will go quickly, but this is an atom, and at the center we have an atomic nucleus. Okay, the size of an atom is very small, 10 to minus 10 meter or 1 angstrom. So I draw some numbers here. So an ant is 1,000th of a human being, let's say, but a pollen of a flower is 1,000th times smaller than an ant. In this way, you can go down, down scale, smaller scale. And then in the end, an atom is something like that. So, but the atomic nucleus is even more smaller object. Okay, so an atom is something like this, but the atomic nucleus is even more 10,000 times smaller than atomic nucleus. An atom, sorry. Okay, so we deal with this kind of tiny physical object, and I will explain how it is interesting. Okay, so here is a famous example, in Japan. So the scale difference between an atom and the atomic nucleus is something like that. So a baseball park, the scale is something like this. And at the center of this baseball park, we put a pinball here. So this is a kind of scale difference between an atom, size of an atom and the atomic nucleus. Okay, another example is here. So I took from Google Map. So this is your university, and here, okay, typical size, okay, 170 centimeter, okay. Then you can imagine 10,000 times larger area, something like this. So this is so if you are an atomic nucleus, the electrons are moving somewhere there. So this, you can see some feeling. Okay, so this is the difference. Another example is here. So this is the Earth, and the size of the Earth is, okay, let's say this size. And then the four orders of magnitude smaller area is something like this. So it is kind of typical size of university campus. Okay, so anyway, so this is a scale difference, to tell you the size of the atomic nucleus. So it is very tiny object at the center of an atom. And today I will try to convince you why it is interesting to study this kind of tiny object. So the message, I say that this is a takeaway message in my talk. So the message today is the following. So nuclear physics is actually ubiquitous. So it has highly transdisciplinary character, connecting different scales of physics in the universe. So from the elementary particles, condensed matter physics, and astrophysics and cosmology. Okay, so today I will try to tell you, after the seminar, you can understand part of this statement. Okay, so let me start with small scale. So the relation between atomic nuclei and quarks, the elementary particles. Okay, so, but I will skip the details. So this is the so-called the standard model of elementary particles. So there are elementary particles like quarks and leptons. Those are fermions. And there are some generations, first, second, and third generations. And we know that we can describe very well this kind of interaction between these particles using the gauge theory. And in the gauge theory, we describe the interaction by exchange of some gauge bosons. In case of quarks, the strong interaction we can describe using some exchange of gluons based on quantum chromodynamics, QCD. But anyway, in our, in nuclear physics, especially at low energy, what I'm interested in, we do not treat quarkonic degrees of freedom. So what does it mean? So in high energy, we need to treat quarks and gluons, but at low energy, we don't have to treat those degrees of freedom. So let me explain. So this is a quarks, elementary particles, but let's go from quarks to the world of hadrons. Okay, so this is a famous QCD phase diagram. So this is the phase diagram for many quark system. Okay, so this is similar to the phase diagram for, let's say, the water. So at low temperature, water becomes solid, I mean ice, and at high temperature, it becomes the vapor. So the gas phase, like something like that. So as you can see, so this axis shows the temperature, and this horizontal axis is the density. So at high temperature, so it corresponds to the early universe. We have some kind of plasma of quarks and gluons, which we call quark-gluon plasma, QZP. So in high energy physics, actually, we study this property of QZP using some heavy ion collider. And also at high density, so the density is so high, so then the boundary of these hadrons are overlapping, and then we have some degrees of freedom of quarks and gluons. So in this extreme limits, we may have the quarks and gluons, but at low temperature or low density region, we have the world of hadrons. So what is this? So hadrons are the composite particles of quarks. So which is divided into two classes. So one is baryons, which is made of 3 quarks, and the other is mesons, which is made of quark and anti-quark, so 2 quarks. So actually the protons and neutrons, the building block in the atomic nucleus, is made kind of baryons, okay, something like that. So so at high energy, we study as I mentioned, in high energy collision, we study the QZP, so to explore the evolution of the universe in this region. And also, so this is, I will explain a bit later, the neutron stars. In the core of neutron star, we may have some quark matter, and it is related to the color superconductivity. So anyways, the atomic nuclei corresponds to something like this, somewhere like there. Okay. Okay, so let me continue. So here I put some animation. So this is the animation from relativistic heavy ion collider RIC. So, but this is a high energy collision. So due to the Lorentz contraction, we have this kind of pancake-shaped atomic nuclei, and they collide very violently. And because of this high energy, we destroy atomic nucleus, and there appear the QZP, quarks and gluons, and many particles are created. But as you can see, at this high energy, we totally destroy atomic nuclei, and this is not my interest. Okay, this is too high energy. So what we do? So we study low energy nuclear physics. So it means that we treat neutrons and protons as building blocks. So what we study is the following. So it is a quantum many-body problem of fermions interacting through the nuclear force. So it is quite similar to the condensed matter physics, where they treat electrons, which is also the kind of fermions, and properties of many fermionic systems. So it is similar to condensed matter physics, but the interaction and the scale and time scale are different. Okay, so let me repeat. So it is true that the neutrons and protons are made of quarks, but at low energy, we don't have to treat the degrees of freedom inside the nucleon. So we treat those fermions, neutrons and protons, as a building block without any structure, and they are interacting through some typical interaction, the nuclear force. So here I draw some schematic shape of the central part of the nuclear force. So at short distance, less than 0.5 femtometer, we have strong repulsion. So repulsive core, that's something like this. And at short distance, up to 2 Fermi, 2 femtometer, something like this, we have some short range attractive interaction. So it is quite different from the electromagnetic Coulomb interaction. So this makes the nuclear system different from some other condensed matter physics. Okay. So I skip the details, but the nuclear force is interesting in the sense that it shows some complex state dependence, spin orbit interaction, tensor interaction, and so on. So it makes the many body system complex but interesting. Okay, so the point is here. So we study quantum many body problem of fermions. Okay, so this is my point. So now let me introduce some selected topical issue in nuclear physics. So I would say the state of the art of nuclear physics is kind of voyage towards the limit of existence of nuclei. So what does it mean? So here I put some image. So this is a Great Wall in China, as you may know. So and this express, nuclear physicists' view of the nuclear landscape. So I skip the details, but there is some kind of stability line, the so-called beta stability line. So for some number of neutrons and protons, we have typically stable nuclei. And around it, we have many structures, as you can see from this photo. So there are some trees, some kind of structures, and so on. And this explains the nuclear physicist's view of nuclear structure. So in each stable atomic nucleus exhibit different properties, structural properties, and excitation properties, and so on. And it is very interesting quantum mechanical systems. And this figure expresses the continent of stability, let's say. And it means that there are stable nuclei which has very long lifetime, which is longer than the age of the universe. So in principle, it is stable. It doesn't decay. So such a stable nuclei have been well studied experimentally and theoretically. But in recent years, we have more sophisticated technology. And now we are sailing towards the edge of nuclear landscape. So the situation is something like that. So here you can see this continent is the stability, continent of stability here that I showed in the previous slide. And apart from that, we have some sea of unstable nuclei. So actually stable nuclei is roughly 300. And we have many, some theory predicts 7,000 or even more unstable nuclei exist. So we have many unexplored territory in the nuclear landscape like this. Excuse me. So at the light nuclei, we have already reached some kind of limit of existence. And we have found that the structure of unstable nuclei is particularly different from the stable nuclei. For instance, we have some kind of halo structure. It means that like a halo of the moon, you can see the moon at the night. Then you can see some cloud, some shining cloud around the moon, diffusive shining light. It is called halo. And for unstable neutron-rich nuclei, we have some kind of halo structure with neutrons around the atomic nucleus. So something like this. So we have some different properties of atomic nuclei in the region of unstable nuclei. And now we are trying to understand in a unified way, not only the stable nuclei, but also many unstable nuclei in a unified way. So this is a state of the art of nuclear physics today. So more scientifically, the situation is described by this nuclear chart. So this is a map of nuclei. So this figure shows the neutron number here and proton number here. So each point corresponds to different atomic nuclei. So that by specifying neutron number n and the proton number z, we have different kind of atomic nuclei. So this black dots corresponds to stable nuclei, and these colored boxes correspond to unstable nuclei which have been produced experimentally. And this yellow or cyan colored region corresponds to unstable nuclei which have been predicted to exist by some theory but have not been produced to date. So as you can see, we have this unexplored area of unstable nuclei. So it is typically important because, for instance, okay, so there is a kind of nucleosynthesis. So this is a explosive process during some stellar explosion. This is the R process nucleosynthesis. So in this explosive scenario, we have a rapid neutron capture processes so that it goes in this way. So it goes in the neutron-rich region. So to understand better the origin of elements in these heavy elements, we have to study, we have to understand better the properties of neutron-rich nuclei in this region. And the other topic is this something like this. So, okay, so this proton number is equal to the atomic number. So it characterizes chemical properties of the atom. Okay, so far we know that the proton number up to 118 organeson exists, but we don't know how much go further, how much we can go further. So what is the heaviest elements that can exist in nature? This is a fundamental question that we should address by synthesizing super heavy nuclei in this region. Okay, this is the other example of the state of the art of nuclear physics today. Okay, so let me introduce this subject. So synthesis of super heavy elements. And this is also relevant to the chemistry. Okay, so let me explain. So, you know, this alchemy is the kind of attempt to change the property of elements by some chemical reactions. But you know that we cannot do something like that. But at the nuclear level, we can do this alchemy. What does it mean? So this is an example. So here is a tin, and here is a copper. And by merging these two, we can create gold. Okay, so this is some kind of alchemy, but at a nuclear level. So what does it mean? So tin is has a protons, 50 number of protons, and the copper has an atomic number 29. So if we add these two, we have 79 protons, which corresponds to the atomic number of gold. Okay, so at the nuclear level, we can collide two atomic nuclei and making a merger or nuclear fusion reaction, we can create different elements. Okay, so this is an alchemy, let's say alchemy. So how can we do that? So we use some kind of accelerator facilities to make the fusion reaction. So a typical example is in Japan. So this is the RIB factory at Riken. Okay, so this is the underground accelerator facility, and you can see the size of the accelerator. You can imagine. So this is a kind of superconducting ring cyclotron, and the size is something like this. So it is quite a large object. And you can see this accelerator is quite huge. And actually, this is a world-leading factory of unstable nuclei. So since 2007, around 2007, so this factory, I mean, this RIBA factory could produce a lot of unstable nuclei. And we have been reading this plays a major role in extending our understanding of unstable nuclei. Okay, so in the case of super heavy element synthesis, so let's start with this topic. I mean, let's explain this fact. So periodic table is growing. So I don't know if you know this fact. So in the past, typically when I learn about the periodic table, there are many missing elements in this region. But nowadays we have no missing elements up to 7 period. So actually in 2016 we have added 4 new elements: nihonium, moscovium, tennessine, and organeson in this row. So after that, we have completed up to the 7th row, and you may say the periodic table is complete, but we don't know actually how much we can go further. So we may have element 119, 120, and so on. And we are trying to produce such an element and study chemical properties and try to understand better the nature. So, so this, let me quickly mention here. So this shows the periodic table with flags that shows the country of discovery of those elements. So here, element 113 was synthesized in Japan at the Riken. So according to this, we got the naming license, so we put the name nihonium. So nihonium is named after Nihon. I mean, Nihon is a Japanese way of expression of the Japan. So we put the name nihonium here. So this is very important achievement, and we are trying to go further. Okay, so I will skip this. Okay, so let me digest how it is difficult to synthesize a nihonium or super heavy elements. Okay, so experiment was started in 2003 in September. And after 100 days irradiation of some nuclear beam, so it is a bunch of nuclei, I mean 10 to 12 nuclei per second. So it is a so huge number of nuclei, and we had a lot of collisions. But after 100 days of nuclear reactions, we got one event, only one event of synthesis of element 113. And further, so after 100 days irradiation, after 1 year, I mean, not almost 1 year, we had second event. So it is, you can see it is very hard to synthesize such a super heavy new element. But this was unfortunate because of the fact that the last decay chain ended up with fission. Fission is some division of heavy nuclei into 2 different nuclei. And this is a minor process, and it was not enough, I mean, to get a naming license. Okay. But so we continued the experiment, and after 360 days irradiation, but you can see there was 7 years from this second event. So we continued 7 years of experiment, and then we got the third event. So it decays quite quickly, but at the end, the decay chain goes to some known data, agrees with known data, which alpha decays into some known elements. And after these three observations, we got the naming license, and that was the achievement. But as you can see, this is very, very difficult experiment. And also it is very hard to describe theoretically. So it is very difficult challenge. Okay, so this shows some cartoon of towards the synthesis of the super heavy elements. So we know that some kind of hot fusion reaction is successful to synthesize heavy elements, but we don't know actually how to go further. So how to synthesize one element 119, 120, and further, we don't know yet. So we are trying to understand, and as a nucleus theorist, we are trying to predict, go further. Maybe not the fusion reaction, but many, different way. So we need theoretical predictions. So this is a typical example, of my research work. So I did some kind of quantum mechanical simulation for super heavy element synthesis. So we described time evolution of wave functions of neutrons and protons on a supercomputer. So in this way, we can follow in real time and real space the reaction dynamics microscopically based on the many body approach. So, okay, so this is a kind of example of, of the state of the art of nuclear science today. So element of to synthesize the super heavy elements. Okay, so this is one topic. And okay, so let me change the topic. So let me take a short break, as it is a quite complex talk. And I put some pedagogical, break. Okay, so as I mentioned, the nucleus is tiny object, very tiny object, and it is governed by the so-called quantum mechanics. So it is different from the classical mechanics. So how different? So there are a lot of wonders in the microscopic scale, I would say. So here is an example of the wonder of quantum mechanics. So if you already learn quantum mechanics, you can understand well, but let me explain. So I don't know if you are familiar with baseball. So he is Shohei Ohtani. He is now playing the Angels as a both pitcher and batter. Okay, so this is a duality. Anyway, so here you can imagine to put some kind of wall with some slit here. In classical mechanics, the ball throws from here goes, pass through each one of those of slits. So one or only left slit or right slit. This is natural in our daily life. But in quantum mechanics, it is different. So this is a typical, famous example. So this is a double slit experiment of electrons. So so here is electrons going this way and enters to the slit. And so this is actual snapshot. So after the experiment, you can see creation of some kind of pattern here. So this is due to the fact that the electrons have some kind of properties of waves according to the quantum mechanics. So this is an interference of water waves. So you can see, so you know that there are some places that we have more larger amplitude and a smaller amplitude, something like that. So this is what happened here. So it is completely different from the classical mechanics, and that's why we I mean, we are interested in the quantum mechanics. Another example here. So another example is something like that. So, okay, this is the photo of theme park. So this is a jet coaster. And, you know, by using this energy of, I mean, having this object at the higher level, we can gain the kinetic energy, and we get some, we can feel some acceleration, and we can enjoy this machine. But imagine that if we have higher bump here. So in classical mechanics, because of the energy conservation, you know that we can not overcome this bump here. So it is not enjoyable. But in quantum mechanics, actually there is a kind of tunneling effect. So we can, there is a part of wave function, I mean, part of some small probability that penetrate through this bump. So even in this case, in this kind of situation, we can go the other side of this bump and continue this, I mean, enjoy this. Okay. So that was some kind of example. And let me turn to the main subject, but it is related to that example. So as I mentioned, at the frontier of nuclear physics, we are now sailing toward the edge of the nuclear landscape. But the interesting point, I think, that the theoretical physics is so, I mean, we have degrees of freedom that we can imagine anything. So we can imagine that, okay, let's gather a lot of huge number of neutrons. What happens? Then gravity makes a bound object. And okay, so actually we have some kind of edge, I mean, or we have some, the boundary of stable finite nuclei. But actually, if we gather a huge number of neutrons, we can make a kind of planet or a star, so which is called neutron star, which is related to the quantum mechanical phenomena, and which can exist actually in the universe. Okay, so let me move to the physics of neutron star. So you may think that it is quite different from the tiny object, atomic nuclei, and kind of stellar object, neutron star, but actually it is closely related. So let me explain. So here I put the kind of example in daily life. So the sun. So the sun is shining, as you know, but it is the source of energy is actually nuclear fusion reaction. So nuclear fusion reaction takes place inside the star, and this is a source of the energy, and this is a subject of nuclear physics apparently. So what happens in the sun? So in the sun we have kind of, I mean, the so-called proton-proton chain, PP chain, as depicted here, but you can neglect the details. So what happens here? So we have 4 protons before the reaction, and after some reactions, we produce a helium nucleus, or the so-called alpha particle. So what happened is 4 protons became a helium nucleus, and then if we compare the mass of these objects before and after the reaction, actually after the reaction, the mass is lighter. So 4 protons is heavier than the helium nucleus. So what does it mean? So as you know, according to the Einstein, this equation, the mass is equivalent to the energy. So it means that this energy of reduced mass was generated, emitted from after the reaction. So this is the source of energy in the shining star. And let me emphasize that protons have positive charge. So there is acting the Coulomb repulsion. So because of the Coulomb repulsion, we cannot make the fusion reaction in classical sense. Actually, what I mentioned, the quantum tunneling makes the penetration of the barrier through the Coulomb barrier, and the charged nuclei can get fused. So quantum mechanical effect is in the star. Okay. So someone is asking the question or not? May I continue, or do you want to ask something? Okay. If you have a question, please let me know. Okay, so let me continue. So here, oh, no, I don't know. So please let me know. So here I explain the life cycle of a light star. So starting from some gas of interstellar dust, because of the gravitational attraction, we have some kind of protostar, and it may eventually we have formation of the star. And inside the star, due to the high pressure, we have some nuclear reaction like PP chain, and after that we form kind of red giant. And when the reaction stopped, then it goes to in this path, or it undergoes some gravitational collapse, making a white dwarf. So actually, after 5 billion years, the sun will be a white dwarf, by the way. So anyway, this is the life cycle of a light star. So let me explain what happens in the heavier star. So to explain this, let me introduce the stability of nuclei. So this is a kind of well-known famous plot in nuclear physics. So this figure shows the binding energy per nucleon as a function of mass number. So binding energy means that the larger the binding energy, the element is more stable. So it shows that we have some kind of peak here. So it indicates that the iron nucleus is the most stable element. So it means that the lighter nuclei, lighter than iron, they get energy, they gain energy by nuclear fusion reaction, as I mentioned in the PP chain. So up to iron, we can have some fusion reactions to gain energy, to release the energy. So this is the energy source of the shining star. And in case of heavy nuclei, they gain energy by nuclear fission. So it means that before the fission, it is heavier than after the fission. So actually, after fission, the nuclei lose the energy, lose the mass, and because of this reduction of the mass, we have release of the energy. So this is the energy source of nuclear plants, actually. So anyway, so this fusion reaction is relevant to the stellar reaction inside the heavy star. Okay, so in case of the massive star, we have reactions inside the star up to iron. So what happens is a chain of nuclear fusion reactions. So not only helium, I mean pp chain, but also we have chain of nuclear fusion reactions to form the ionic core. So after that, we have kind of onionic structure, something like this. And because the iron is the most stable element, we do not have, the fusion reaction cannot take place after forming the iron core. So what happens? So after formation of the iron core, the pressure at the center decreases. And after that, it cannot sustain the gravitational force, and we have some supernova explosion in the end. So this is a typical example of the Crab nebula. Okay. So anyway, the massive star after forming the ionic core, we have supernova explosion. And after the supernova, as a remnant, we may have a black hole for the massive star. But if the mass is not heavy enough to form a black hole, we have a peculiar object called neutron star. So neutron star, from our nuclear physicist view, the neutron star is an ultra heavy super neutron rich nucleus. So we can study a lot of physics in the neutron star. So this is a paradise for nuclear physicists. So, and again, let me mention some wonders in quantum mechanics. So, as you may know, and as you may not know, so in quantum mechanics, there are two kinds of particles called fermion and boson. And they show quite different properties. So fermions can, stay one state. State is kind of seat for one particle. So if one particle, one fermion stay at one state, another particle cannot stay at the same level, same seat. So this is just an image. But in case of bosons, they can take the same state by many particles. So this is very, very different properties. And why I introduced this one? So actually, these bosonic properties make superconductivity and superfluidity as a macroscopic quantum phenomenon. I skipped the detail, but this is related to this bosonic structure, character. And actually, this fermionic character makes the neutron star or white dwarf. So because of this peculiar property, we have kind of pressure, quantum mechanical pressure that can sustain the gravitational force. This is the reason why we have neutron stars or white dwarf in the universe. So here is again quantum mechanics inside the star. Okay. So here I show some schematic view of the neutron star structure. So there are many layers depending on the density, and I skip the detail, but there is some kind of solid crust and kind of liquid uniform matter and some many unknown core region, which includes the quark matter. But anyway, so I will talk about the inner crust region, and let me introduce one of peculiar property in the nuclear crust, that's so-called nuclear pasta. So what does it mean? So nuclear pasta is this kind of inhomogeneous structure inside the nuclear matter. So as you can see, depending on the density, the system prefer kind of bubble structure and the rod structure and kind of slab structure. And this is because of the similarity between some Italian gnocchi, lasagna, spaghettis, we call this collectively as nuclear pasta phase. And since this is a kind of crystalline structure, it is related to the solid state physics. And I skipped the detail, but we are now developing some time-dependent band theory to describe the pasta phase microscopic way. Okay. And it is related to various astrophysical phenomena, the so-called neutron star glitch or some kind of quasi-periodic oscillation. Let me explain here briefly. So what is quasi-periodic oscillation? So this is similar to the seismology in the case of the Earth. So seismology is the study inside the Earth according to the propagation of earthquakes. So we cannot see directly the inside the Earth, but by analyzing the propagation of the earthquake, the vibration, oscillation, then we can get the information about the inside structure of the Earth. So we can adapt the same thing to the neutron star. So neutron star is in the universe, and we cannot see directly the inside the neutron star. But after some explosive reaction, we have some kind of oscillation of the neutron star. Okay, so, and by analyzing the oscillation, we can see, you can learn the inside of the neutron star. So this is a recent publication related to this work. And it shows that there are many oscillation modes, but using some Fourier analysis, there are several typical oscillation frequencies. And they could explain a lot of frequencies according to the vibration of pasta structure. So this is an indication, direct indication or evidence of the presence of the nuclear pasta. So this in the study is related to this kind of stellar phenomenon. So by the way, how long can I continue? Should I stop after 1 hour, or we can go a bit further?
Yes, you can continue, please.
Okay, so let me continue. Okay, so the other example is neutron star glitch. So let me introduce what is neutron star glitch. So actually, I don't know you know this object, pulsar. Pulsar is actually rotating neutron star. So after the supernova explosion, as a remnant, we have a dense stellar object that I introduced, the neutron star. And you can imagine that because of the angular momentum conservation, so, okay, the star is kind of rotating huge object. And after the collapse, gravitation collapse, we have small massive object. And you know, the figure skater, you can imagine figure skater. So they can change the arm. So if they shrink, the compact shape, then they can rotate faster. So the same thing happens here. So after the supernova explosion, we have dense small object, and it is because of the angular momentum conservation, it is rotating very quickly. So how quickly? So it is the part. Okay, so and if we observe this rotating object from the Earth, it is like pulsing. So we can detect this pulse from this rotating neutron star. And the period, frequency of this rotation is as fast as milliseconds. Okay, so period is milliseconds. So you can imagine 10 kilometer huge object is rotating 1,000 times per second. So it is an extremely fast and extreme condition. So anyway, this is a rotating neutron star, the pulsar. So now, what is a glitch? So let me explain. So this is a typical example of Vira pulsar. So here I show the plot showing the period as a function of time. So this period means the rotation, period of the rotation of the Vira pulsar. And this time you can see the year, something like this. Okay, so because of the electromagnetic radiation that I showed in the previous slide, the pulsar is losing energy. So the period is increasing. So this is a spin down. But if you look at very carefully, you can find some noise here. So this is actually the glitch. So what happens? So actually, once per several years, quasi-periodically, we have kind of spin up of the rotating neutron star. And you know, the neutron star is in the universe, an isolated object. So to change the rotation period or rotation frequency, something must happen inside the neutron star. So this is the point. So this is the glitch. And what happened? So there are several scenarios. One is starquake. The other is vortex mediated glitch. And okay, so in various reasons, this starquake, some kind of earthquake inside the neutron star, it cannot explain the quasi-periodic nature of the glitch. But so now we consider that this vortex mediated scenario is more reliable. So what is a vortex? So this vortex is actually quantum mechanical vortex. And this is related to the nuclear superfluidity. Okay, so let me explain. So what is quantum vortices? But I skipped the mathematical introduction and I just give you an idea. So in daily life, okay, so this is a classical fluid, let's say, and you can stir by some spoon, and you can make any size or any speed of rotating flow. So this is just a classical fluid mechanics. But in case of quantum mechanical fluid, it is not the case. So this is the snapshot of rotating superfluid. This is actually experimentally taken snapshot. So when superfluid is rotating, then we have an array of quantized vortices, something like this. So you can see some dots here. This shows some density depression, and at each point we have rotating small quantized vortices. So this is due to some quantum mechanical nature of superfluidity, but this is nature. I mean, this is a fact. Okay, so let me show some interesting video. So this is an experimentally taken video of rotating superfluid, and experimentalists try to visualize the quantized vortices. So they put some hydrogen particles inside the superfluid, and using some laser beam, I mean shining the light, they visualize this presence of line-shaped object. And this is, we believe that this is a formation of quantized vortices in superfluid, rotating superfluid. Okay, so this is an example. I mean, they exist in nature. So, okay, let me explain. So why quantum vortices are important? So, okay, as I mentioned, in rotating superfluid, we have an array of quantized vortices. And the number of vortices depends on the rotation speed. Now, because the neutron star, inside the neutron star, actually we have superfluid neutrons, which I skipped the explanation, but because of the nuclear attractive interaction, they can make a Cooper pair and they form a superfluid. And as I mentioned, neutron star is rotating. So inside the neutron star, there must be a huge number of quantized vortices inside the neutron star. A huge number means 10 to 18 vortices. Okay. So inside the neutron star, we have a huge number of quantized vortices. Okay, then, yeah. Okay, so let me explain the glitch. So this shows schematically the rotation frequency as a function of time. So because of as I explained, because of electromagnetic radiation, the neutron star spins down. So the rotation frequency is decreasing. So this is what we observe actually. But if there is a superfluid component, actually there should be some decoupled superfluid components, and it takes preserves the angular momentum in the form of quantized vortices. And if vortices are pinned onto the solid crust, they store the angular momentum in this way. So the solid crust, the whole star is spinning down, but the superfluid component stores the angular momentum. And at some point, a catastrophic unpinning event could take place. And then this angular momentum can transfer to the rest of the star. Then it shows sudden increase of the rotation frequency, and it repeats periodically. So it explains the quasi-periodic occurrence of the glitches, and also explains many other properties. So we believe that the glitches are caused by the dynamics of quantized vortices inside the neutron star. Okay, so now maybe I will skip the details, but so nowadays, okay, I can skip the many details. I skipped the details here, computation part. So anyway, so recently using some supercomputer, we studied this pinning mechanism. So there are many other scenarios, to study. So dynamics of glitches and trigger mechanism, pinning mechanism. But with microscopic theory, we try to understand this pinning mechanism. And I show simulation, here. So this blue line shows the center position of rotating, quantized vortex of neutrons, superfluid neutrons. And here there is an atomic nucleus in the neutron star crust. So based on the time-dependent microscopic quantum mechanical calculation, we simulate the dynamics of quantized vortices and the nucleus, and extracted the interaction between vortex and the nucleus. And in this at this density, it is actually repulsive according to our simulation. So anyway, let me move on to the final topic, and this is the end of my talk. Okay, so last but not least, the important subject is neutron star merger and gravitational waves and nucleosynthesis. So as I mentioned, the iron is the most stable element. So, but you know that there are a lot of elements that are heavier than iron, like gold and silver or platinum and so on. So how they were produced in nature. So this is known, it is known that this is one of the unsolved problems in physics. But I would say we have learned a lot about it. So recently, you know that it is nowadays possible to detect gravitational waves on the Earth. So it changed the research of the physics recently. So now we are in a new era of multi-messenger astronomy. So there are, okay, so this is a part of a catalog that shows gravitational wave signals in 2015 to 2017. And the most striking event is here. So this is the gravitational wave observed in 2017, August 17. So this is associated with the binary neutron star merger. So merger of two neutron stars. Okay, so this is striking event. So what is interesting is here. So not only the gravitational wave after the merger of neutron star, but also the electromagnetic waves are detected after the merger of neutron star. And analysis of these two provides the fact, evidence that the elements heavier than iron were actually synthesized during the merger of neutron stars. And also how they deform during the merger and how the gravitational waves change during the merger event provides us information about the inside of neutron star. So a lot of new things can be explored with the gravitational wave detection, and this is at the frontier of nuclear, not only nuclear physics, but also in physics generally. And I just show typical animation for the simulation of R-process nucleosynthesis during the neutron star merger. So you can see this. So this is a part of nuclear chart, and during the this shows during the neutron star merger. So because of the rapid neutron capture process, we can synthesize atomic nuclei up to here, and after that beta decay takes place and it cools down to the stable elements. So this is a simulation, and you can see this. So this blue dots shows the solar abundance. So abundance of elements in our solar system. So this is an observation in our universe, in our solar system. And this red line shows the simulation. And as you can see, the simulation of nuclear R-process nucleosynthesis can explain the solar abundance very nicely. So in this way, we are now knowing the details of R-process nucleosynthesis, the origin of the heavy elements. But we are now trying to understand better the details. Okay, so this is also the current, state of the art of nuclear physics today. Okay, so let me summarize my talk. So the topic, what I'd like to tell you today is our exciting adventure to study the nuclear physics using some time-dependent microscopic approaches. So those are some pictures. So as I mentioned, not only stable nuclei, we are now trying to reach the limit of existence of the finite nuclei. And also we are trying to understand the stellar dense object called neutron star. And those are closely related to the various fields of science. So in my opinion, what is interesting in nuclear physics is a transdisciplinary character. Okay, so it is related to the not only elementary physics like quarks and gluons, but also condensed matter physics, solid state physics, and also astrophysics and cosmology and so on. So, and also what I showed today is a quite very tiny part of the huge field. So if you are interested, you can study the nuclear physics. So again, so this is a takeaway message. So this, I hope you a bit of you. I mean, you are convinced that nuclear physics is ubiquitous and it shows very wide. I mean, it is related to very wide field of physics in various ways. Okay, so this is the end of my talk. And finally, I put two messages to the undergraduate course student and PhD students. So one message is here. So maybe you can learn, but you can read. But let me digest. So my point is the following. So all the subjects you learn are indispensable. So I think in the undergraduate course, you learn a lot of things: classical mechanics, thermodynamics, quantum mechanics, electromagnetism, and so on. And at first, it is quite difficult. I mean, and it is independent to each other. But actually, it is the equipment all necessary to understand the nature. So, and at the end, after all completing all the subjects, I promise you that you can see the beauty of the nature that may change the rest of your life. So please study hard, be ambitious, and have fun of physics. Okay, this is one message for undergraduate course student. And the other message is that for graduate course student. Okay, so this is related to my experience. So you can see, but the point is the following. So when I was a master's and PhD course students, the subject was not promising for me. I mean, at least at first sight, it was not promising. And when I was a master course student, okay, oh, I got wrong results. Okay, this is not wrong, not well, not going well. But after that, I study hard and try to, where is it? Deepest ever achieved, and try to understand the, the physics behind. Then at the end, I found that it is promising, and I got many new results at the end of the PhD course. So please be confident. Anything can be interesting. So please believe yourself and try to study hard what you are studying. It will be indispensable experience in the rest of your life. Okay. So sorry for taking the time. So this is the end of my talk. Thank you for your attention, and I will be glad to ask any questions.
Yes, thank you, Professor SEKIZAWA. There will be some questions from our students. Dr. Rajan Sani, could you please share the questions raised by the students?
So anyone can ask questions, but the sign is raising your hand.
Professor SEKIZAWA, are you seeing the questions raised in the chat box? Or should I read? Should I read questions raised by the participants in the chat box? Hello.
Hi.
Hello.
Hi. Does anyone have questions?
Yes. Yes.
So anyone can ask. Or should I
Thank
pick
you,
up?
Sekizawa-san.
Yeah. Okay.
Let me. Okay, it was nice talk, and I see you skipped 1 or 2 slides about the details of supercomputing, right?
Yes.
So probably I just asked on for the students. Actually, there are many undergraduate and postgraduate students attending this. So it's good to take 2 minutes to explain how this supercomputing looks like.
Okay.
Not a mathematical, just to see the
Yeah.
how you deal with this.
Okay, thank you. Okay, so you can disregard the detail of equation, but what we need to solve is huge number of 3D coupled nonlinear partial differential equations. Huge number means it could be 1 million of coupled nonlinear partial differential equation. So it is not solvable by hand, of course, and we need supercomputer. So how to deal with this equation? So actually we have access to some machines, but typically we use GPU, some graphic processing unit, GPU. So how it is possible to parallelize why we use GPUs? So, okay, let me give you an idea. So CPU that I mean, you are familiar with this. So every laptop or computer, I mean, has CPU. And this is like a very fast sushi production machine. Let me take Japanese example, but this is imaginary machine. Okay, so this horrible sushi production machine can produce sushi very, very fast. Okay. Then it is not accessible by hand. I mean, human beings. We cannot reach this speed. Impossible. So this is very quick sushi production machine. So imagine that if we gather manpower, so if we gather, I mean, huge number of people and try to make the sushi in collaboration in those people, then at some point, if number is sufficient, we can beat this horrible sushi production machine. So this is a image what GPU looks like. So GPU, in a single GPU, we can launch thousands of computing units. Okay, so it makes possible to parallelize a huge number of parallelization of the computation. Okay, so how we parallelize the equation? So actually this equation is local in space. I mean, the R corresponds to the coordinate or in the 3-dimensional space. And at each grid points, we assign each computing unit. So in this way, by parallelizing this computational grid points by using huge number of threads, GPUs, we can efficiently parallelize the code and we can achieve the huge gain in the computation time. So that was the main idea for the supercomputing.
Thank you.
Yeah.
So probably there are some questions in chat box. Professor Sugit can read it.
Yes. The first question is there any possibility of finding the naturally occurring super heavy elements in stars?
Oh, that's a good question. So we don't know yet, but there are some research that analyze the, how to say, I forgot, meteorites. Meteorites means some rock coming from the universe, you know. So by analyzing such a object, they found that some signature of very heavy, super heavy elements entered into this rock. It means that during the explosion, I mean, for instance, the neutron star merger, few super heavy elements may be produced and they traveled in the universe and entered into the meteorites, and they put some signature inside it. So we don't know, but it may be possible in some rare case to form the super heavy elements during the R process. And there are some indication, but not sure yet.
Okay. Then next question is by one our undergraduate student. That is, what causes the gravitational pressure which leads to collapse the neutron stars?
What causes the gravitational pressure which leads to
collapse the neutron star?
So gravitational force is just because of the massive, because the star is very heavy. So we have gravitational attraction towards the center of the star. But as I mentioned somewhere here, where is it? So there is a quantum mechanical pressure called degenerate pressure. Where is it? Excuse me. Okay, so this is a pressure associated with fermionic character of particle. I mean, neutrons, protons, electrons, they are fermions. So they are fermions here. So what does it mean? So it means that one state for one particle means they cannot move at the same velocity. So it means that if we gather a huge number of fermionic particles, like inside the neutron star, they has to gain kinetic energy because of this property. So this generates some kind of pressure at the center of the core, and it compensate the gravitational attraction. But after formation of the ionic core, the nuclear fusion reaction stops. So we do not have nuclear fusion reaction at the center, and this causes the, after formation of the ionic core, the pressure decreases and it cannot compensate the gravitational attraction, and in the end, it goes to the supernova explosion.
Then next is, can we take Z is equal to 120 as a limit on the superhabitability that can be getted in the laboratory?
No. So we don't know yet. So the next because it will be difficult to go further, we are going step by step. So since we have so far we could synthesize up to element 118, the next will be 119 and 120, but we don't know if 121, 122 and so on exist. So we are just, I mentioned as a next step from the organism, but we don't know if we go further. So that's the fundamental question we need to address by theory and experiment in future.
Okay, then could you please throw some light on the quantum vortex? Some students are asking the physical meaning of that.
Physical meaning of quantum vortex.
Yes,
Okay.
yes, yes.
Okay, so maybe I have some slides. Okay. Yeah. So, okay, let me try to explain. So what is quantized vortex? So, okay, so this delta is the so-called order parameter of superfluidity. So you can neglect the detail, but it is it depends on the coordinate and time, and it is a complex quantity. So complex means it has magnitude and the phase. Okay, so okay, this is a order parameter that characterizes the superfluid, and we can define superfluid velocity in this formula. So it is associated with the gradient of the phase here. So this is a superfluid velocity. And from this, you can easily see that the vorticity, which is defined as a rotation of the velocity, is 0. Because this is a potential flow. So or you can say that the gradient of rotation of the gradient is mathematically 0. So vorticity is 0 in superfluid. Okay, so superfluid is irrotational. So how quantized vortices exist in superfluid? And actually, this is true only for the case of normal superfluid. So it means that unless there is no topological defect, it is 0. But if we have topological defect, it can be non-zero value. So let me explain. So what is topology? So topology is a concept that characterizes, to divide, to categorize objects according to the number of some points, this kind of peculiar points. So according to topology, this sphere and the core is equivalent because we can continuously change the shape from one to the other. And here, donut shape and the mug cup is also equivalent because we can continuously change from one to the other. But we cannot go from core to donuts because there is some hole here. So this hole distinguishes a mug from a core. So this is the so-called topological defect. So imagine the superfluid, and we make a hole at which superfluidity is lost. So this is a topological defect in the superfluid. Then, so you can use the Stokes' theorem to make this area integral to the line integral, and you can insert this equation, and you can find that this line integral must be the multiple of 2 pi, because this phase at the same spatial point must be equivalent. So when we make a closed circle, it must be returned to the same equivalent phase. So it must be multiple of 2 pi. So this is the so-called quantization of circulation. So this is a quantum mechanical results associated with the superfluidity. So it means that the velocity field is quantized because of this. So since the phase rotates by 2 pi and the gradient of the phase is a velocity field. It corresponds to the rotating supercurrent around the topological defect here. So this is a quantum vortex, and it is stabilized because of this topological character. So this is a, naive explanation of the what is quantized vortices.
Okay.
Okay.
Then next is supernova explosion no more a candidate for our process?
So yes or no. Certainly during the supernova explosion, there must occur R process. So R process must occur during the supernova explosion. So in this sense, in this sense, the supernova is also a candidate for the R process. Okay, there must be, because during the supernova explosion, there are a lot of neutrons at extremely dense environment. So we must have R process nuclear synthesis. The question is if it is enough to explain the observed R process abundance in the universe. So for some research, it is not enough to explain some part of heavy elements. So the scenario is something like this. So at early stage of the universe, there are not enough number of neutron stars. In such a case, the supernova explosions are the main source of R process elements. But after billions of years, we have a sufficient number of neutron stars, and there appear neutron star mergers. And the neutron stars produce those heavy elements. So there are two sources. So both neutron stars mergers and supernovas contribute to the creation of the heavy elements, but currently the dominant process is the neutron star merger, I would say.
Yes, then next is what kind of detectors are used to detect the gravitational waves?
What? To detect what?
To detect the
gravitational
waves, yes.
Oh, that I didn't prepare, but okay. So gravitational wave. Okay, let's see. So this is a merger of neutron stars. Okay, okay. So gravitational waves is some waves that propagates. The waves of the space and time. So you know that according to the Einstein's general relativity, we can describe the gravitational gravity by some curving space-time, and the gravitational wave is a propagation of the wave of the space-time. So when two neutron stars merge, they make some ripples of the space-time. So how to say? So during the merger, so okay, I cannot write. So during the merger, so they rotate some kind of this dumbbell-shaped object is rotating very quickly. Then it emits gravitational waves, and it propagates at the speed of light and reaches the Earth. Okay. Then since this is change of the space-time, I mean the oscillation wave of the space-time, if we put, I mean the length of the space changes due to the gravitation wave. It means that maybe I can try. So this is just a detector that shows just to check some interference between lights, and there are some kind of mirrors here and here and here there, and then they can tune to I mean, if we change the length between mirrors, the length that light travels changes. So it affects the interference pattern. Okay. Then when gravitational wave comes here, it changes the space-time in this region. So because of the gravitational wave, this length between the mirror changes due to the oscillation of the space-time. And then they can measure the change of the interference pattern, and in this way they can measure the gravitation wave. But the point is the length is very, very long. I don't remember the actual length, but it is huge. I don't know, kilometer or I don't remember, but it is very, very large interferometer, or you can search for LIGO, something like that. Interferometer gravitational observatory, something like that. But anyway, so we can detect in such a way the change of the oscillation of the space-time through the interference pattern of the lights.
Yes, last two questions.
Okay.
Without taking too much time. The first is, can superfluidity occur at high temperature? High temperature neutron star.
Okay, so it depends on the temperature. Okay. Sorry. Oh. Sorry, it's tax. But anyway, so to answer the question, okay. Sorry. What happened? Okay. Okay, sorry. So the superfluidity, of course, depends on the temperature. And if I have the slide, yeah. Okay, so but it doesn't show the dependence. So of course, okay, imagine the superconductor in the laboratory, and it also, of course, we need to go lower and lower temperature. At very low temperature, we have superconductivity because the superconductivity or superfluidity emerge at very low temperature. So there is of course for nuclear systems the critical temperature at which superfluidity is lost, and in case of neutron star class, it is about 10 to 10 Kelvin. So inside the proto-neutron star, I mean, after the formation of the neutron star, it is quite hot, and their superfluidity would be gone. But in usual normal neutron star, it is cool enough to have superfluidity. I mean, below the 10 to 10 Kelvin, typically 10 to 8, 10 to 9, and so on. So it is at below, I mean, normal neutron star, it is below the critical temperature, but there exists certainly the critical temperature.
Okay. Then one last question, already addressed, but student is asking again, why there are only 3 generations of quarks, and what is the particular parameter on the basis of which we differentiate these generations?
The first question is why there's 3 quarks, 3 generation. That is difficult question because yeah, that is a difficult question because it is related to why nature chooses so. But maybe in the end, using kind of string theory that unifies the 3 forces and the gravitational force, then one may show why there appear only 3 generations, but it is difficult to answer, I think, because we don't know. I mean, the nature chosen this.
Okay, there are still some questions. Probably
Yep.
I will send by email, and without taking too much time, I think we have to close it. And depending upon availability of time, you can answer one by one, and I can circulate among the participants. Is it okay?
Yes.
Okay. Now I request my colleague, Dr. Rajan Sani, to convey the thanks to the speaker and the organizers. Rajan Sani, sir, please.
Thank you, sir. I would like to thank Honorable Vice Chancellor Professor Gurmail Singh ji for his kind permission to organize today's webinar. I further extend my thanks to today's speaker, Professor SEKIZAWA, for his wonderful talk on the behalf of all the faculty members and the participants. We are also thankful to all the external participants from 24 different national and international institutes. Some of them are University of Padova, Italy, Mumbai University, Punjab University, Chandigarh, MMU Maulana, Guru Nanak Dev University, Amritsar, and Central University, Kashmir. I'm also thankful to all the faculty members and students of Akal University for attending this webinar. Thanks is also due to the IT department of Akal University and Delhi office for their support. We are also thankful to Dr. Jagjit Singh, who became instrumental in organizing this event. Thank you, sir.
So thank you, Professor SEKIZAWA. Hope we will listen to you again sometime in the near future.
Yes.
Thank you. Thank you very much.
Thank you.
Okay, bye.
Yep. So may I leave the meeting, or if there's some?
Yes, you may please leave the meeting.